So, okay, let's move on. So next speaker is going to talk about quasi-normal mode approach to non-thermal fixed points. The stage is yours.
So let me start by thanking the organization for giving me the opportunity to talk. I had hoped to be there in person, but I had some issues with the visa, so it's going to be an online talk. So today I'm going to talk about a quasi-normal mode approach to non-thermal fixed points, and this will be mainly based on this work that appeared this year by myself and my supervisor, Michael Heller, and some ideas that are work in progress. Okay, so let me start with the general introduction. So the motivation for this talk is so we want to describe dynamics. So we cannot consider just equilibrium states. So we have to consider pre-thermodynamics, and one nice framework to describe dynamics is hydrodynamics. But hydrodynamics, of course, has its limits of applicability, and we want to use, for example, linearized hydrodynamics. You need to consider systems that are locally close to equilibrium. And then you have a very universal description of these pre-thermodynamics. However, once you're far from this equilibrium, notion of local equilibrium, non-hydrodynamic effects dominate, and it seems that in that case, a general description of dynamics becomes hopeless because non-hydrodynamic effects are non-universal. So I want to pose the question if some form of hydrodynamic behavior is possible far from equilibrium. And I guess there are multiple directions to go to answer this question, but I want to talk about an idea that was proposed in this paper, also by my supervisor Michael Heller and collaborators, where they considered the dynamics near non-thermal fixed points. So, of course, I have to introduce what non-thermal fixed points are, and non-thermal fixed points are far from equilibrium, attractive stages in the evolution of systems. So the idea is that if you initialize a system in a certain way that is very non-thermal, if you initialize them in different ways that are very non-thermal, these differences in initial conditions, they don't matter at late enough times, and the evolution becomes the same for these different initial conditions. And at this point, where the evolution becomes the same, the dynamics simplify, and the associated dynamics, the dynamics are associated with some scaling behavior in time. So you have some kind of momentum redistribution that happens in a way through cascades, like with turbulence and these kind of things, and you can capture it with the rescaling of time. So the non-thermal initial conditions have this notion of overoccupation. So you put a lot of energy in one side of your spectrum, for example, so a lot of energy in the infrared, and then the redistribution of energy will happen through the scaling. And these are mostly found in weak coupling theories, so or in large N resummations, but they haven't been found, for example, in holography or these strongly coupled theories. So as of now, I would say this is a very weak coupling picture on thermodynamics. But why do we care about these non-thermal fixed points? Or why are they interesting to study? So I already said one aspect which I find very nice is that if you start from different initial conditions, the dynamics will become the same for different at a certain point in time. So this means that if you can describe these dynamics, you don't have to care too much about these initial conditions, and you can actually say general things about a stage of the dynamics of the system that is far from equilibrium. But there is also a notion of universality associated to these non-thermal fixed points that is the same as universality near, for example, second-order phase transitions, where if you're close to the critical temperature, physical observable quantity scale with this temperature in some power law manner with exponents, that can be the same for different macroscopic theories. So here as well, you have this scaling, but now in time with exponents, and these exponents can also be the same for different macroscopic theories. So then there is another nice aspect where you can study a simple example from one universality class to learn about the broader universality class. So this universality is highlighted also in the fact that these non-thermal fixed points were first, I think, thought about in the context of heavy ion collisions. So in very early stages in weakly coupled thermalization pictures of heavy ion collisions, such a non-thermal fixed point behavior is expected to occur. And this has been studied numerically in kinetic theory simulations, but also in classical statistical simulations, and they indeed find the dynamics associated to non-thermal fixed point behavior. And more recently, this kind of behavior has also been signaled in Gautam experiments. So there are experiments, for example, in Cambridge and Vienna, where people consider Bose gases, and then they initialize them in some non-thermal way, and then they exactly see this scaling behavior that you would expect from non-thermal fixed points, also for different initial conditions. And then one last nice aspect of these non-thermal fixed points is that they are some kind of semi-analytically soluble corner of the non-thermodynamics. So there are some statements you can make analytically about this behavior that is quite striking, because in general, out of equilibrium physics, it's hard to do analytical calculations with. So before I go a bit more into detail of what the dynamics are near a non-thermal fixed point, I want to discuss kinetic theory, because this is the language I'm going to use throughout this talk to describe these physical phenomena. So kinetic theories are based on weakly coupled quasi-particle description, and the quantity or the object that you evolve is the distribution function of these particles. So this says the probability of finding an amount of particles at a certain point with a certain momenta in time. And then the dynamics are governed by the Boltzmann equation. So the left-hand side captures the change in the distribution function, and the right-hand side encodes the collisions between these quasi-particles. And this you can get from, for example, quantum field theory calculations. You can calculate matrix elements, scattering element, and then you can set up this kernel. But the reason why I will use kinetic theory is because it captures this main feature of non-thermal fixed point, namely this scaling in time. So the main feature of a non-thermal fixed point is actually self-similarity. So with self-similarity, I mean, if you consider this distribution function, so non-thermal fixed points are isotropic and homogeneous, so it only depends on time and the magnitude of momentum. Then when you're at the non-thermal fixed point, the dynamics for this object actually simplifies, and it becomes it becomes a function of momentum that is rescaled with some power law in time, and then a time-dependent amplitude in front. So you see that instead of two variables, time and momenta, you only have to know this one function, the scaling function, as a function of one variable, and this one variable is the rescaled moment. And then these exponents, alpha, beta, and the scaling function, they are independent of the initial conditions. And then the idea is that different initial conditions at one point will all follow this behavior. So I show a plot here of this self-similarity, and this is actually a figure that I took from a paper that appeared in Nature, and it was from a Gautam experiment done by the Babbage group in Cambridge. So they also considered different initial conditions, so the different shapes, and they measured the distribution function of those gas particles, and then when you express it as a function of momentum, you see in time that the amplitude grows and the momentum scale moves to the infrared. So this is the cascade I was talking about. And then if you rescale the distribution function with this time-dependent amplitude to kill the time dependence, and you express it in function of this rescale momentum, you actually see one static curve for all the initial conditions. And this is this scaling function. So in this picture, it seems like the system is static. So now before I go over to the things I want to discuss, I want to talk about one last aspect of non-terminal fixed points, namely pre-scaling. And the idea is that this previous expression of self-similarity is a bit too restrictive, and you can actually have a more generalized version of the self-similarity, and then this will be visible at earlier times. So this is an example I took from a numerical simulation I made, where the distribution function is expressed as a function of momentum in the z direction, and time flows like this. So the amplitude drops and the momentum scale moves to the left. And if you would rescale it with the usual power laws in time, like the ones I just explained in the previous slide, you don't see it collapsed onto a single scaling function. And this is expected to happen at later times, but it hasn't happened yet at these times. While if I use some more general time-dependent functions, which you can find, which they should be, and then I rescale amplitude and momenta with time, then I find a complete collapse already at early times. So this is the idea of pre-scaling. And this was first signaled in this paper, and then worked out in more detail in this paper by my supervisor and collaborators. And so I already said the idea is that there is some generalized time dependence in the rescalings. And then the time-dependent functions are related by conserved quantities. So there's only one independent time-dependent function you actually have to find. And then the whole point of this analysis is that if you plug this ansatz into the equations of motion, all terms should scale in the same way in time when you view everything in terms of this rescale moment. So usually this will not be the case, but then if you initialize the system or you consider it in the correct regime, so this was where the overoccupation comes into play, you can actually ensure that this happens. So this overoccupation, for example, makes sure that if you have cubic terms and quadratic terms, that the cubic terms dominate, and then you can actually make every term scale in the same way. And then it comes out that this is the form of the generalized self-similarity functions, time-dependent functions. And this is actually very logical and physically expected, because the equations of motion are time, translation, invariant, and there is no special origin of time in these equations. But in the self-similar expressions where you just consider the power law, then E equals 0 is special because it is like a fixed point in your rescaling. So either you just at 0 or you're at infinity, depending on the sign of your exponent. And it's weird that here t equals 0 is special, while here it's arbitrary. So by considering this form, you actually allow the system to pick the correct origin of time for the self-similar. So this was the physical motivation for prescaling, and it will come back later in the talk. So this is why I flashed it. And then a last important part of this is that this was also experimentally verified in this paper that I also already showed figures from. And there, what they did was you consider the self-similar expression at momentum 0. So then you just have power law and some constant amplitude. And now if you take this quantity to 1 over the exponent of the power law, you just have a linear function in time. So this is showcased here in the sketch, that if you consider the correct exponent, you should see a linear curve in time. And then where it crosses the 0 on the y-axis, this is then the other offset in time. So they did these simulation, these experiments with different initial conditions, and they find different offsets in time, but they do find that all of them have an offset in time. So they find this prescaling effect, and they show its initial condition dependent. So this was just to show that they can actually measure these things in the lab, and that these are physical effects that are there in the quantum system. So now I will discuss some ideas I worked out in this paper together with Michael Heller. And the paper was called Quasinormal modes of nonthermal fixed points. So I want to introduce the concept of quasinormal modes. And this concept actually comes from black hole physics. And they're relevant for thermalization through the ADS-CFT correspondence. So the ADS-CFT formalism, the thermal state on the ADS boundary is dual to a static black hole's ADS spacetime. And you can then test thermalization by perturbing this black hole spacetime. And then this black hole spacetime is expected to return to its static state. And how this returns then describes how a system returns to equilibrium, a strongly coupled system returns to equilibrium. So when you perturb a black hole spacetime, the black hole starts ringing. So what this means is that you can decompose the physical time-dependent effects there in terms of a sum of exponential functions with characteristic frequencies, these omega, and time. So if your omega has an imaginary part, it leads to growth or decay. And if it has a real part, it leads to oscillation. So the idea is then if you know these characteristic frequencies, you can describe what happens near equilibrium. And another idea is that because they describe relaxation, the magnitude of the imaginary part of these frequencies then actually creates some hierarchy in the importance of these quasinormal modes at late times. So the ones with the smallest imaginary part, they will dominate at later times because they have not decayed away as much as the ones with a larger imaginary. So if you want to say something general about an approach to equilibrium, I think this is the best thing to consider, because at late times, if one mode dominates, this could be like some more universal description, while if there are more modes, this depends more on the initial condition. Then these quasinormal modes also encode hydrodynamic transport coefficients, and you can consider so you see hydrodynamic effects from these modes as well. And the idea is that hydrodynamic behavior appears at late times when you consider the system over large distance scales, because then these modes actually become gapless. So these are the longest lived modes, and they are associated to conserved quantities. So that's why they are so long lived, because the conserved quantities cannot just dissipate away. So this was some motivation why we want to study quasinormal modes, and now we can try to do a similar analysis as you can do in a black hole spacetime, but then for this nonthermal fixed point. So the idea we had is to consider this self-similar form of the distribution function. And as I said before, if you scale out the time-dependent amplitude and consider it in the rescaled momentum, then it seems to become static. So we will call this the static frame, and then your background effectively becomes time independent. And then the picture is very similar to equilibrium or the black hole case, where you expect perturbations to relax back to this static background. So we consider the perturbation on top of this scaling function in this static background. And then we plug this into the Boltzmann equation, and we see what the characteristic quantity frequencies, actually what they are and what they tell us about the system. Now, when you play this game and you plug this, the linearized perturbation into the Boltzmann equation, you get an equation for the perturbation, of course, but the time dependence on the left-hand side is of this form. So the time-dependent operator is time times the derivative of time. And then on the right-hand side, you just have some linear operator. that only depends on this rescale moment. So when you see such a form of the equation, this signals to you that you should not decompose the perturbation in terms of a sum of exponential functions, but rather in the sum of power law functions because of this time-dependent operator. So this is one of the first results of this paper was that instead of the signal that tells you about the approach to non-thermal fixed point, instead of being characterized by exponential functions with characteristic frequencies, it's you should decompose in terms of power laws with characteristic exponents. And then these exponents and this momentum dependence, they are the Quasinormal modes of the non-thermal fixed point. And when you plug this back into the equation, you get an eigenvalue problem for these frequencies, which one can solve in the specific setup to learn about how this non-thermal fixed point is approached. So I want to highlight again the difference between the results near equilibrium and near the non-thermal fixed point. So near equilibrium, on the left-hand side, you will just have a time derivative, and this tells you should decompose into exponentials. So here we had time times the time derivative, and this says you should decompose in terms of power loss. And then the linear operator on the right-hand side in equilibrium is just your linearized collision kernel. While now, for the non-thermal fixed point, you actually pick up additional terms that are associated to this rescaling of your frame. And this is because your background was inherently time dependent, and we only made it time independent by rescale. So there is this difference here, and this plays a role because the normal like zero modes are associated to conserved quantities, and it's very easy to get them from the collision kernel. You know what you would expect there, but here there are these additional terms that don't make it as straightforward as the equilibrium. So you have to work a bit harder to understand. So I want to test these findings or these predictions in some form of a kinetic theory. So to this end, I considered the Fokker-Planck kinetic theory. So this kinetic theory describes how gluons undergo elastic scatterings. And the idea is that in the QCD, full QCD elastic kernel, the small angle scatterings actually dominate. And then you can derive this equation, which is the Fokker-Planck-like equation. And it just goes down to diffusion and momentum. So there are some terms that I closed out because this term has some time dependence, which is understood that we want to neglect for the non-thermal fixed point analysis. And the effect of this term is in these papers, so we'll just neglect this term. And then these terms actually would break this scaling analysis that I said before, where you want every term to scale in the same way in time. So if you would plug in this self-similar ansatz, and you would have this term here is a quadratic term, this would be a linear term in F. If you don't drop one of them, you would have different scaling in time, and the self-similar ansatz wouldn't be a solution of your equation of motion. Now, by assuming overoccupation, you assume this term dominates, so you can drop this term, and also in this IA and IB, which are integrals of the distribution function, you can do the same. And then you can find the non-thermal fixed point solution with exponents beta equals -1.7, and alpha is 4 times beta, which is constrained by energy conservation. So this is the model I will be able to calculate the Quasinormal mode spectrum. So first, I want to talk a bit about this role of conservation laws in constraining the dynamics, because I think it's important, since this is also what actually gives you hydrodynamic effects, that there are conserved quantities. And the way the self-similarity is constrained is in the following sense. So you consider energy density, which is this integral moment of your distribution function. And here you just have the dispersion relation of your quasi-particles you're considering. So for example, for massless gluons, we would put P, so Z equals 1. And then you assume this is the self-similar non-thermal fixed point form. So you get the time-dependent amplitude, and then it becomes a function of rescale momenta. So in the integral, you rescale momenta, and you get these time-dependent functions in front. Now this is just an integral over some demi-variable, which is this rescale momenta. So this is a constant value if you integrate from 0 to infinity. And this is time dependent, and you can then make the whole energy density constant if you choose alpha to be proportional to beta in this way. So this was where this fork came from in the previous slide. Now, if you do the same analysis, but you consider on top of this similar non-thermal fixed point solution a perturbation, then you have, of course, your energy density is the energy density of the scaling function plus the energy density of the perturbation, which is time dependent. Now, we know what the time dependence of the perturbation looks like. It's this power law with some characteristic frequency or exponent. So if we plug this into the expression for energy density, we again get some constant and the power law before it. And if we demand that this is constant, because energy density should be constant, then there are two ways for this to be constant. Either the frequency is 0, and we have some kind of 0 mode or gapless mode, or the energy density of the perturbation is 0. And this was important because if you don't impose this condition, you didn't get a nice result for the Quasinormal mode spectrum. So the Quasinormal mode spectrum is obtained by solving the eigenvalue problem that I described earlier. And the result for the Fokker-Planck kinetic theory is the following. So you have the 0 mode, and then you have some other modes that lie deeper in the complex plane, and they are all purely imaginary, and they all result in decay. So I took the same convention as usual, where the negative imaginary values result in decay. So this highlights that we have the spectrum of an attractor. So the non-thermal fixed point is attractive, and this is an explanation why the different initial conditions approach the same behavior, because all the initial condition information is encoded in these other Quasinormal modes, and they decay away over time. And then there are two modes that I singled out. So the 0 mode, which is related to a conserved quantity, and in the expression you can easily understand that this TRF, the physical quantity, shouldn't matter on this reference scale and the power laws. So you can get actually the value of this frequency, but also the momentum dependence by changing the reference time in your expressions for the scaling function. And then we exactly found the same frequency, and we also exactly found numerically the same momentum dependence. It's in the paper if people are interested. But then there is also another mode that lies here at -7i. In this mode, we could also analytically predict, because it's associated to this B-scaling effect, which I discussed before. So if you consider the pre-scaling form and you do a shift in this offset time, then you exactly get that there should be a power law, should be a Quasinormal mode with an exponent that is base value. And also there, the momentum dependence can be predicted, and there also we found an exact match. It's associated momentum dependent with this Quasinormal mode. So for us, the fact that prescaling could be observed in an experiment, and we find prescaling as one of these Quasinormal modes, is an indication that maybe these other modes could also be observed in experiments, and this is something we would like to work towards. But now I want to talk about something that might be more interesting and relevant for this program, namely this idea of hydrodynamics near a non-thermal fixed point. And this is actually based on a paper by my collaborator, by my supervisor and his collaborators, Jürgen Bergers, Dynamical, and Timo Prijs. And the idea is the following. So standard inequilibrium hydrodynamics, I think some of the assumptions I go into it is that the equilibrium state is attractive. So at late times you expect to reach equilibrium, and that and you also know that equilibrium is homogeneous, and there are conservation laws that constrain that. So if you would have some inhomogeneity that carries a conserved quantity, this cannot just dissipate away, but it needs to be transported to make the system homogeneous again and approach equilibrium. And this is where hydrodynamic transport comes in. But these three points that I highlighted here, they are also fulfilled for a non-thermal fixed point. So we just showed in our previous action and in our paper that the non-thermal fixed point seems to be an attractive state of the dynamics. It is a homogeneous solution of the equation of motion, and the dynamics are constrained by conservation. So one could hope then that the hydrodynamic effects would also be present around this point. So I already said that this hydrodynamic behavior arises because the conserved quantities cannot dissipate, and at a linearized level, when you consider spatial dependence, if you look at very large of a very large distance scale, so the spatial momenta goes to 0, then there will be modes that become gapless, and these are the hydrodynamic modes. So they determine the late time behavior. And we also signaled one gapless mode in our previous analysis. So this also strengthens the hope that there might be some hydrodynamic effects around the non-thermal fixed point. So in this paper, they also considered kinetic theory, because this is a natural language to describe this non-thermal fixed point. And then you can derive a fluid dynamical theory from kinetic theory by expanding around some background state. So you do the background state plus some perturbation on top of it, and then you can you can approximate this distribution function in terms of its moments. Of course, you need an infinite amount of integral moments to fully describe this distribution function. So you truncate it at some point, and then you get these equations that are like fluid-like. Now, the only assumption that comes into this construction is that the background, apart from the other ones that would allow you to do consider hydrodynamics, of course, but the only other assumption is that the background is isotropic. Now, the non-thermal fixed point background is also isotropic, so you can actually just play the same game and plug the non-thermal fixed point solution to the construction. But the difference is, of course, that now the background is dynamical, because we're not in equilibrium. And then the point of this paper was to figure out how this actually changes the hydrodynamic behavior. So you consider in hydrodynamics, you consider the energy momentum tensor, which you decompose into the ideal fluid part, with energy density and pressure, and the shear stress tensor, which captures dissipative effects. So this should go to 0, and then the system is described by ideal hydrodynamics. But this shear stress tensor is expressed again in terms of a distribution function. And from the Boltzmann equation, with this expanding it into moments and then truncating, you can actually get an equation for the shear stress tensor. And when you do this around the non-thermal fixed point, you get the following equation for this, the equation of motion for the shear stress tensor. And then it actually looks exactly the same as in near equilibrium Israel-Stewart hydrodynamics. So these ellipses are nonlinear terms. But the difference is that the transport coefficients are time dependent now. So it seems like the structure is the same, but the time dependent background imposes some time dependence into the transport coefficients. So they could also run simulations of kinetic theory, and then measure the shear viscosity, this transport coefficient, and the relaxation time, and compare it to the predictions that they could calculate from the previous equation of motion, and they find actually that they should both grow linearly in time. And in the simulations, they find indeed that it seems like it follows this trend of linear growth in time at late time. So another thing they did was to consider the linearized hydrodynamic equations and see what the effect is on this dispersion relation of the hydrodynamic modes. And so when you consider linearized hydrodynamics, you go over to do spatial Fourier transform. So instead of working in position, you just work with spatial momentum. And in equilibrium, you do also Fourier transform in frequency space, but for the non-thermal fixed point, because they expect the transport coefficients to be time dependent, they decided to work with a more generalized Fourier transform, where you now integrate over the time dependent frequency. And then the idea of a gapless mode still is there, that hydrodynamic modes are the ones where this time-dependent frequency goes to zero as the spatial momentum to zero. So when you do this spatial Fourier transform and work with this time-dependent Fourier transform, what they find is that the dispersion relations become time-independent and identical to the near equilibrium counterparts if frequency and spatial momentum are rescaled in this way. So the spatial momentum should go as 1 over t, and then the rescale momentum also is 1 over t. And if you do this rescaling, everything comes out time independent in the frame where you consider this rescale momentum to be constant. So for example, if you take the shear channel and you consider the dispersion, the equation you get for the frequency, we can get the dispersion relation by solving this equation. And then there are two solutions. And for the limits where k goes to 0, you find the usual diffusion mode. So it goes as k squared. And you see indeed that if k goes to 0, this goes to 0. So this is the hydrodynamic mode. And you also find this non-hydrodynamic mode because this is a constant when k goes to 0. But now, because we had a different Fourier transform, when you plug this in and you reinstate time dependence, the time dependence of the linear perturbations looks a bit different. So for the non-thermal fixed point, when you plug this one back into the Fourier transform, you actually get that it's an exponential of t squared times k squared, which is different from the near equilibrium case, where it's just an exponential of k squared times t. So this is usual diffusion. So this signals that the physics is a bit different there. And then you could indeed observe the time dependence in the shear viscosity. And you see indeed that the expression looks again similar, but now the shear viscosity is time dependent. So this is where the time dependent transport coefficients come into play. So this was for the hydrodynamic effect, but then for the non-hydrodynamic effect, the time dependence is completely different. And if you plug this back into the Fourier transform, you actually get power law decay instead of the usual exponential decay you would expect. So this finding is completely in agreement with the finding of our previous paper, where the zero mode, so we worked, of course, at the limit k going to 0. So we just had a zero mode, which would be this one. And then transient modes are power laws that decay in this way. So I now want to very briefly discuss some idea I wanted to work out, but didn't have time enough to fully work out. So this is just work in progress. And I wanted to explain these findings of this paper that considered hydrodynamics the non-thermal fixed point, but then starting from the full Boltzmann equation, so not having to truncate anything or make approximations further. So the idea is very similar to the normal quasinormal mode calculation I did, but now you just assume that the the perturbations have spatial dependence. And having gained some inspiration from the previous paper, the spatial Fourier transform remains the same, but then we also do this more general time-dependent Fourier transform. And if you do this, you get an equation with different terms, and then these terms scale differently in time. So most of the terms that are associated to the non-thermal fixed point background scale as 1/t. And then you have a term that is proportional to k, no time dependence, and a term that is proportional to this time-dependent frequency. So the game you normally play is that all terms should scale in the same way, and then you can eliminate explicit time dependence. So we can play this game here again and rescale the frequency and the momentum in this way, and this is exactly the same way as was considered in the paper I discussed in the previous section. So this seems to confirm their findings, but from the full Boltzmann equation.
You're running over time, so if you can wrap up.
Yes, so I have like 5 slides, I think. I'll quickly go. So the idea is just that when you, again, the equations look a bit different compared to near equilibrium, but one can play the same game. And the main difference is that by rescaling k, we generated a new term, which is this one. So it has k times the derivative of k. And if you would try to solve this in some kind of derivative expansion in k, you would get different terms at every order. And this is something I want to investigate in future work. So now I come to my conclusions, where in this talk, I hope to convince you all that the non-thermal fixed points are some interesting phenomena to study for the reasons of universality, experimentally accessible, and they have some degree of solubility. A lot of the ideas of near equilibrium physics can be applied, like this linearized, calculating linearized spectrum, like Quasinormal modes and considering hydrodynamics, but it seems to lead to different physical effects, like these power law transients and time-dependent transfer coefficients. And for an outlook, it would be nice to work these ideas out with the spatial dependence a bit more, and then check these findings against simulations, or even work it out in models that are relevant for Gautam experiments to make predictions that they could actually measure. And then a last interesting thing could be to consider this non-thermal fixed point in a longitudinally boosted invariant expanding background, because this is also a setup where you can study hydrodynamic effects near equilibrium. So with this, I will conclude, and thank you for your attention.
Nice talk. Now it's time for questions. Yes.
And thank you very much for the nice presentation. Like there is something that is confusing me, but probably I overlooking something. Okay, so you were mentioning that the conservation laws are fixed in the exponent, but
Yes.
Which conservation law are you using? Because if you just use the energy, I think this already fixes the relative exponent between what is outside and inside the function. But if I'm conserving also the number of particles, then the set is over constrained. This is actually connected with some plots to show at the beginning of the experimental implementation that I think that is on a momentum distribution, for which if the system is closed, should conserve both the energy and number of particles. So the scaling, if what I'm saying is correct, and this you have to tell me, of course, the scaling cannot be exact on the whole distribution.
Yes, so this is actually a very good point. So I'm trying to find the plot you were mentioning, but this is a very good point, because indeed, if you have like these two conservation lengths, like particle number and energy density, then it's over constrained, and you would have different relations between alpha and beta. So what happens in systems where this actually is the case is that in the infrared, there is one kind of non-thermal fixed point self-similarity associated to the conservation of particle density, and then one non-thermal fixed point self-similar scaling as in the UV that is separate. So there seems that it's like a separation of scales between where most of the particles are distributed in momentum space, and where the energy is distributed. And then these two seem to be decoupled, and they both have their own self-similar scaling.
So if I can rephrase my own words, it's as if you're looking at momentum distribution, some part will appear to scale in a certain way, another
Yes.
part in another way, but of course there will be a crossover between the regions.
Yes, and this crossover is indeed then harder to describe, but this is what happens, and this is what people see in experiments. And if I can say something more about this, so this paper I discussed that considers hydrodynamics around the non-thermal fixed point only considered conservation of energy momentum tensor. But if you want to describe, for example, an infrared cascade, the conserved quantity there is the particle number. So then you would just have hydrodynamics of conserved.
Maybe if you can also comment what you would expect in a case where you have more conservation laws. Like, because we try to look at a similar measurement in 1D experiment that is integrable, that has a lot of conservation laws. And of course, scaling was not really working because we couldn't have a synchronous scaling. Now I understand what you mean in terms of number of particles and energy that you have to scale separately momentum distribution. But in that case, we have also additional conservation laws. Do you think there is something interesting? What we should look at to see the scaling?
Yeah, so I don't think you always expect, if you, for example, have two conservation laws, it's not like you always expect these two cascades. So you have to push the system in a regime where there is this separation so that these two cascades can emerge. So if you would have even more conserved quantities, then it might just be over-constrained and scaling would not work, or it might work in some fine-tuned way. But I would have to look at it to say more, I think.
Okay, but don't worry. Thank you very much for taking your time thinking about it. Thank you.
Thank you. Thank you for the questions.
Any other question?
Yeah, okay, maybe this is related. So what are the conditions to observe these nonlinear, non-thermal fixed points?
Yes, so so it seems in the experiments what you have to do is to initialize the system in a way that it's overoccupied. So you put, for example, more particles in a part of the distribution than the thermal distribution would be able to account for. And then you also need these conservation laws to constrain the dynamics such that the momentum is redistributed in this way. So to me, it seems like this overoccupation and the presence of conservation laws are the only two things you need in order to see it. But then this, of course, only happens in weak coupling theories. So it might just be a weakly coupled effect as well. But there's not a lot of assumptions that come into it.
Then so for example, you could think that you start from initial state that has all the weight at zero momentum, and then you expect to see a cascade, a larger momentum. And
Yes.
that's when you see this fixed point, right?
Yes. So yeah, normally what they do in experiments, for example, they try to start from some kind of box initial condition, where the height of the box is very high compared to if you would put all this energy and particles in a thermal distribution function, and then yeah.
And the scattering is two body, or
yeah. So the scattering is two body, but so when people talk about this in QCD kinetic theory for heavy ion collisions, they also consider the inelastic scatterings, and there the scaling is actually the same as the elastic ones. So it's not like inelastic scatterings break it, but then you don't have particle number conservation. But maybe you have some other conservation. So then you would have one cascade, but you could have it with inelastic scattering.
Is there any? Okay. You have it. Okay, Vir.
A bit confused by how you got power law relaxation out of the Boltzmann equation. So could you just specifically the time derivative being replaced by t times the time derivative?
Yes. So you're confused about this expression?
How can you get two answers out of the Boltzmann equation? It makes one prediction. So what are you assuming to get the t times partial t?
So for the so I get this t times partial t because you put in this scaling, self-similar scaling function, so the non-terminal fixed point function.
But then aren't you assuming your conclusion by putting in the self-similar scaling to begin with?
Yeah, so okay, so the point of this analysis is that if you put in this in the Boltzmann equation, you can show that it's a solution of the equation if you assume over occupation, so you drop indeed some of these terms that I tried to explain. But this doesn't mean that the system would evolve towards this. So then I just plug in this solution with some linear perturbation and consider what this linear perturbation around the solution wants to do. And then it seems like the perturbations want to decay in power law manner.
Okay, thanks.
Yes, so I get this because of the time dependence of the background. Okay,
I don't see any other questions. So thank you, Matisse, again for the talk. And yeah.
Thank you.
So now there is the break, right? So that's all. So we close the session and the day.